Okay, this video is going to be on all things statistics, and hopefully by the end of the video, you'll be experts at this. It's going to be a long one, but the first thing that I want to do is talk about stats and what you need to know for the exam. So the first thing you want to know on stats is basically your average, your median, your mode, your standard deviation, your range, all of that good stuff that you learned back in middle school. So mean is your average, sum of the data values, divide that by the number of values to get your mean. Median is the middle number. Make sure that you are putting it from least to greatest, then crossing off the data values to get the median. Mode is the data value that appears the most, and standard deviation, which might be new to you guys, basically is the measure of spread of the data points. So this is sometimes called variability or spread. Basically means how spread out are your data points. If it is spread out, then you have a large standard deviation, which means that your data points are far away from the mean. And if you have a small standard deviation, that means your data points are very close to each other, which means that they are basically near the mean. And then a standard deviation of 0 basically means that your data points are all the same, which means it's the mean. And you'll see later on how that goes about. Just a reminder that these notes are in the calendar on Canvas. Box plots are a way to describe or look at the data set. So here is what a box plot looks like. The box plot gives you a summary, and sometimes it's called a 5-number summary. It provides information about a data set. You have your minimum, which is your smallest number in the data set. You have your maximum, which is your largest data in your data set. You have your median, which is the middle, your lower quartile, which is basically your middle number between your minimum and median, which is the bottom 25%. And then you have your upper quartile, which is Q3, and this is your middle number between the median and maximum. Notice how with your box plot, they are split up into 4 equal parts. These 4 equal parts basically represent the percentages in each set. So for example, from minimum to Q1, that's 25%. From Q1 to median, that's another 25%. From median to Q3, that's another 25%. And then from upper quartile to maximum is another 25%. Your IQR is your interquartile range. That is basically the middle 50% of your data set, which is why this big thing is 50%. IQR is also used for spread and variability, which is the same thing as standard deviation. So you should probably check standard deviation and IQR depending on what the question is asking you. Range is the difference between your lowest and highest. And then outliers are going to be your extreme data values that really don't belong in the data set. It's just there for the LOLs. Sometimes on the ELC, they may ask you to remove an outlier and see how it affects the mean or median or standard deviation based off of that outlier being removed. There is a formula to determine if there's an outlier, but honestly, you could just eyeball it to see if it's an outlier or not. So the rule, if your data value is, let's say in Q1 minus 1.5 times IQR, that's your lower outlier. And then if it's greater than Q3 plus 1.5 times IQR, that's your upper outlier. Regression, it's the line that describes how a response variable y changes as an explanatory variable x changes. We often use the regression line to predict the values of y for a value of x. Correlation is basically how the two variables are related, and this is your r value. If you have a positive correlation, that means that your slope of the regression line is positive. If you have a negative correlation, that means the slope of the regression line is negative. And sometimes we don't have no correlation, which means that it's not positive and it's not negative, it's just all over the place, which we'll see on the first practice question. We also have something called a weak correlation. So if your correlation is less than 0.5, that's considered weak. And then we have a strong correlation, and that's considered strong if your correlation is 0.5. A correlation is a number between -1 and 1. So you'll sometimes see like negative 0.87. Negative 0.87 is a negative because we have this negative value right here, and then a negative strong correlation. Strong because 0.87 is greater than 0.5. 0.32 is a weak positive correlation because it's positive. It's a positive number. And 0.32 is considered weak right here. So that's why it's a weak positive correlation. To run a regression line in Desmos, you're going to use the following right here. We'll talk more about this whenever we do talk about the practice problems and how to type that in on the Desmos calculator. And the regression line basically helps you predict values for x and y, which we'll see also later on. The residual is the difference between the predicted value from the regression line and the actual value of your data set. We'll talk more about that later on also. And these graphs are some examples of what a strong positive correlation is. So a strong positive correlation basically means that your data values are near your regression line. A weak positive correlation, you can see that it's positive, but your data points aren't really near the line. A strong negative correlation, same thing. Notice how your points are near the line and it's going down. And then, of course, you have these three, same process. Then we won't talk a lot more about histograms, but the only thing that you might need to focus on is skewness. And basically, it's the measure of asymmetry of a histogram. It doesn't really need to be a histogram. You could also look at skewness based off of a dot plot here. Basically, if your mean is greater than the median, it's skewed to the right. If your mean is equal to the median, it's symmetric. And if mean is less than median, it's skewed to the left. AKA, notice how here, this is skewed to the right because you have more data values on the left than the right side. This is skewed to the left because you have more data sets on the right than you have on the left. And here's another point on standard deviation. It measures the amount of dispersion between the data points, how spread out they are within one another when talking about spread. We usually talk about standard deviation and not the range. Sometimes we also talk about the IQR, but most likely 99% of the time, you'll talk about standard deviation. So here's another example. Here's a practice question. We have a table that shows the number of hours that 10 students practice driving and their scores on a written driving test. And I want to see what the relationship is between the hours driving and their test scores. The first thing that I want to do is actually input this on Desmos. Now make sure that if you are putting this onto Desmos, that it is the North Carolina NC test version. Don't use the regular Desmos because the state does restrict some of the things on the test version. If you click on the plus sign, you can click on table, and then you can enter in the data values that they give you. So it was 3, 5, 2, 6, 7, 1, 2, 7, 1, 7. And then we could say 80, 90, 75, 60, 90, 90, 75, 85, 80, and 100. Now, of course, you can't really see the data values right now, but if you do hit the magnifying glass right here, you could look at the points. And looking at the points already, I kind of know that it's not going to really have a correlation because my data values are all over the place. To verify that, I can create a linear regression. In order to do that, I have to use the regression line formula, which is y1 squiggly mx1 plus b. And the reason why I'm using y1 and x1 is because I have y1 and x1 as my names on the top. The statistics right here gives you r, which is what we're looking for. And notice how r is 0.24, which is less than 0.3. And since it's less than 0.3, I could say that there's basically no correlation. Or if you do want to say that there is a weak correlation, you can, because 0.24 is pretty weak. So here, there's not really a relationship between the hours of students practicing driving and their test scores. On the ELC, they might ask you the effect of removing a point. So looking at these points right here, we can probably remove this point right here. It seems like an outlier. So if I remove 6 and 60, it gives us another regression line. And my regression line is now 0.63. Which means removing 660 actually gave us a stronger positive correlation because now my R value is 0.63. This is what I mean when questions are asking you, hey, remove this outlier and see how it affects the relationship of the variables. So for number 10, there's basically a weak or no correlation. But if you do remove 660, you get a stronger correlation. So this would be a positive strong correlation if we removed 660. For number 13, we have a group of 10 students that are 54 to 56 inches tall and an adult who is 74 inches tall that joins the group. Which statement is true for this situation? Well, the thing is, I don't really know what's what. I only know that 10 of them are 54 to 56 inches tall, and I only know that we have one adult that's 74 inches tall that joins the group. And if you think about this logically, which you'll definitely do on the exam, if I add a person that's 74 inches, obviously my mean or my average is going to go up because that 74 is definitely higher than or greater than 54 and 56. And if you also think about that, that also means that my standard deviation is about to go up because my data values are going to be more spread out. So my mean is going to go up. So this is going to be D. Mode really doesn't affect it because if we add 74, well, 74 isn't really 54 to 56. So you know that your mode has to be between 54 and 56. And then if you talk about the median, well, remember that median's the middle number. And if I think about it, if I have a person that is at 74 and I were to find the median, I'm going to cross out my median from smallest to largest. And if 74 is my largest one, that 74 is going to be marked off first, which means that my median has to be between 54 and 56 again. So that's why our mean is going to be more affected than our median or mode. For number 14, we have Miss Parker determined that the mean test scores for her first period class was an 81 with a standard deviation of 7.06. And then we have her second period class was a mean of 88, but a standard deviation of 8.24. Which conclusion can be made about her students' test scores? Well, remember that if we're talking about standard deviation, we're talking about how spread out it is. Remember that if we have a higher standard deviation, that means our data values are more spread out. And a lower standard deviation means that our standard deviations is going to be clustered together, so less spread out. The lower it is, in this case 7.06, that's going to be less spread out, which is either going to be period 1 or B or D. So it can't be A and it can't be D. And since standard deviation is associated with mean, it can't be D because D is talking about the median. So B is our correct answer here. Okay. Number 28, we have a table and we want to put this table onto the Desmos graphing calculator. So pause this video, put everything on the table, and then make a regression. Once you make the regression line, continue, and then we'll see what the question is asking. So I'm also going to do that. Once I do that, I could click on the magnifying glass right here, just so that I can look at the data set. Make a regression line, so that's y1, squiggly, mx1 plus b. And now I want to look at my regression line and see what's up with it. The question I'm asked is, when the best fit to linear model of this set of data is graphed, which conclusion can be best supported by the residuals? And remember that residuals basically means the difference between your data value and the predicted value, which is your line. So notice how here, my residual is between these data points right here, 92, 92, 95, 95, and 98. They're pretty close to the line, which means that it's a better predictor. Of course, we have these values right here. They're not good predictors because they're not close to the line, which means that we're going to have a greater residual. The lower the residual, the better your relationship is. So like I said here, my regression line, 92, 95, 98 are pretty good. So if I look at my answer choices, I could see that B is my answer, because math test scores are a better predictor of verbal scores for students who had a math score of 89 or higher, as we saw in the graph. 88 or lower, well, that doesn't work because I feel like at 88 or lower, my residual aren't that great compared to your predicted value. And your residual is basically a line from this to your predicted residual line. #29, we have a table below that shows the weights of 8 different bears at a zoo, and if I want to remove the outlier, which is a polar bear, which statement is going to be true? Honestly, for this type of question, you don't really need to type in the data values if you can think logically. If I were to think logically, if I have 1,000 right here and I remove it, then my mean is going to decrease because that 1,000 basically increases your mean. Removing it, you're going to have a cluster of data values that are close to each other, which means that your mean is going to be close to these numbers right here. And if I were to think about the median, well, the median really doesn't affect that much, because if I were to remove 1,000, well, remember that 1,000 is at the very end, and if I were to find the median by hand, that thing's going to be first crossed out. So the median won't be affected that much, but the mean will definitely be affected because your data values right here aren't really at 1,000. So if I look at my answer choices, I know that the mean decreases more than the median, so it can't be B, and it can't be D. So now I need to figure out why it's true. Well, remember that 1,000 is a very high outlier, so that's why it's A. Number 30, we have a box plot for Alana and Terry, and we want to make a conclusion about what's happening. Well, from here, I know that my minimum is 0 and my maximum is 9 for both Alana and Terry. Alana has a median of 6, which I'm going to denote as Q2, and Terry has a median of 4. Remember that this is 25%, this is 25%, this is 25%, and this is 25%. 25, 25, 25, and 25. So A says, Alana ran a more consistent number of miles per day than Terry. Well, the thing is, I don't really know how much Alana or Terry ran each day because my results are congregated because of the box plots. I don't know the individual numbers that Alana and Terry ran, so A can't be right. B says Terry averaged more miles each day than Alana. Well, the thing is, I don't necessarily know what my average is because I don't have separate data values. I only have one big box plot, which tells me the minimum, the maximum, and the median. So it's either going to be C or D. Alana typically ran more miles each day than Terry, or Terry typically ran more miles each day than Alana. Well, if I were to think about typically, it's basically talking about your spread. And remember, your spread is either two things. It's either your standard deviation or your IQR. The thing is, for standard deviation, I can't really find that out because I'm not given the standard deviation and I'm not given a list of data values. So I can't really use standard deviation. But I can use IQR. And remember, IQR is basically your difference of Q3 and Q1, which is your middle 50%. So Alana's middle 50% is right here. And Terry's middle 50% is right here. Terry's IQR is 4, while Alana's IQR is about 5. Which means that Alana typically ran more miles each day than Terry. I could also relate that back to this right here. How relate the box plot by how Alana's median is at 6. So 50% is from 6 to 9. So she probably ran more miles each day than Terry because Terry's 50%, highest 50% would be from 4 to 9. So 30 is C. $40 again, we're looking at we're looking at 3 box plots, and we want to describe the variability of the MPG ratings for the cars. Remember, variability spread, we're looking at standard deviation or IQR. In this case, we have to look at IQR because I don't know what my standard deviation is. Your IQR is going to be your box right here. So if I were to look at sports IQR, '20, 21, 22, 23, 24, 25, 31. So my IQR here is 6. And then my small, if I were to do the same thing, be at 31, 32, 33, 34, which is 3. And then family's IQR, same thing, 1, 2, 3. Just kidding, small, it's not 3. Looks like it was 3, but it's actually 1, 2, 3, 4. So this tells me that sports has a higher IQR, which means it has a higher variability. And you could see that that's true because my spread is kind of large compared to small and a family. Family spread from here to here is smaller than small in sports. So I know that family has a smaller IQR and it definitely has a smaller standard deviation compared to small in sports. So if I were to look at the best statement that describes this, it says there's more variability of small cars in sports cars and family cars. Well, small cars has a variability of 4, but it's less than a sports. So it can't be A. There's more variability in the MPG of the family cars than sports cars and small cars. Well, the thing is, Our family has the smallest or lowest variability among the two smarts and smalls, so it can't be B. C says there's less variability of the MPG of the small cars and the family cars and sports cars. Well, looking at family cars, there's a variability of 3 compared to 4, so it can't be C, which means our answer choice is D. There's less variability of family cars compared to small and sports, which is true because we have this 3 right here, which is the smallest number compared to 4 and 6. We have on 41 a table that shows the attendance at a festival each year since it began in 2002. And if we were to use a linear line of best fit, we want to see what is predicted attendance for the year 2012. Oops, right here. Pause the video and put all of this onto the calculator and create your regression line. And we want to see approximately what's the predicted attendance for the year 2012. But before we do that, let's actually talk about the relationship. Notice how my R value is 0.93. Since my R value is 0.93, I know that it's going to be a strong positive correlation. It's strong because my R value is 0.93, and it's positive because 0.93 is positive. Now, your M and B basically represents slope-intercept form, so if I were to write the regression line, it's going to be 12.77x minus 25554.8. And if you want to look at the predicted attendance for the year 2012, I know that 2012 is my x value. So if 2012 is my x value, I could just say x is equal to 2012 and find my intersection between my 2012 line and the regression line, which is right here. So if I do that, this tells me that my predicted attendance is going to be about 141. Well, 141, but remember that it's in thousands, so it's going to be 141,000. So it's going to be C. Number 46, Carlo believes that the number of hours of video games a student plays is predicted of the student's grade point average, which value represents a correlation coefficient that would strongly support Carlo's belief. So she believes that the number of hours playing a video game is predictive of the student's grade point average. So thinking about that, we want a strong correlation. So in order to get a strong correlation, our number has to be near 1. Ignoring my negatives, the number that's closest to 1 is going to be 0.9. So it's going to be A. So that negative 0.9 basically means that the more hours of video games you play, the smaller your GPA is going to be. Number 3, we have a librarian that recorded the number of books that 10 students checked out, and Carlos checked out 8 books on Tuesday. What is true if Carlos's number is included in the data set? Like like I said earlier, this problem is a logical problem. You really don't need to type this into the calculator, but if you want, you can. But notice how these numbers right here are close to each other, so they're a cluster. And we have 8 books that Carlos checked out, which is basically an outlier. If we have 8 and my data values are clustered between 2 and 5, this basically means that my mean or my average is going to go up, which is C. And if my mean goes up, then my standard deviation also goes up, so it couldn't be B. The median wouldn't necessarily increase because if let's look at 8, well, since 8 is an outlier, that's going to be the first thing off of my list whenever I do find the median. And then the IQR increases. Well, remember that IQR is basically Q3, your differences between Q3 and Q1. And if we have 8 is going to be right here. So it really doesn't really impact the IQR that much. So C, the mean increases. 4, we have the box and whisker plot, which is another name for a box plot. What percentage of people are ages 15 or older? I have 15 right here. And we are looking at this set right here. Looking at that set, well, remember that each individual thing is 25%. So this is 25%, this is 25%, and this is 25%. Which means that there are about 75% of people that are 15 or older based off of this box plot. Number 20. Which set of the data would you expect to have the greatest standard deviation? Remember, greater standard deviation means that your data values are more spread out. So looking at A, the height in centimeters of all of the students in the first grade class in a large elementary school. Well, in a large first grade classroom, we would expect that every student be around the same height. And if you were to expect that, that means that my cluster will be close to one another. So we wouldn't really have a large standard deviation right there. Same thing with B, the heights in centimeters of all the first grade teachers in the elementary school. Well, if I were to look at the first grade teachers and assuming that they're all adults and they stop growing, they should fairly be around the same height. So they're also clustered together, which means that they're going to have a small standard deviation. If I look at C, I have the heights of centimeters of all the first grade students and all of the first grade teachers in the elementary school. And if you think about this, I have, let's say, X amount of people that are first graders that are tiny, tiny. And then I have X amount of teachers that are, taller than the first grade students. And if I were to look at the standard deviation, remember, if I'm looking at spread, well, my spread is going to be from here to here, and that's going to be large, which means our answer choice for number 20 is C, the heights in centimeters of all the first grade students and the teachers in the elementary school will give you the greatest standard deviation. (47) Which equation most closely represents the line of best fit of the scatter plot below? Well, we want the line of best fit this line, so it should look something like this, where your data points close to the line as much as possible. If I look at A and I draw y is equal to x, it's going to look something like this. And you can see that my line doesn't really hit my data values. So it can't be A. Looking at B, if I were to do 3/2 x plus 4, I'm going to go up 3, 1, 2, 3, and then right 2, 1, 2, 3, right 2. It hits some of the points, but not all of them. So this one is greater than most of our data points. So it can't be B. Looking at C, I have a y-intercept at 1 and then a slope of 2/3. So up 2, right 3, 1, 2, 3. Up 2, right 3, 1, 2, 3. Up 2, right 3. This also really doesn't give a line best fit because your data values, once again, aren't really near your line. But if I look at my last answer choice, 3/2, if I go up 3, 1, 2, 3, right 2, 1, 2, 3, right 2, 1, 2, 3, right 2, you could see that it hits most of my data points and it's in the middle of it. So that's why 47 is D. Number 16, we have the data set right here represents the number of hours spent on the internet in a week by students in a mathematics class. Which box plot best represents the data? Well, I don't necessarily know how to create a box plot, but guess what? Desmos can actually create a box plot for you, which is a game changer. Plot these data values on a table. So you're going to go to the calculator, create a table, and plot the points. 5, 6, 7, 8, 9, 9, 9, 10, 12, 14, 17, 17, 18, 19, 19. You won't be able to see it, but that's okay. Once you get your data values onto the table, you can create the box plot. Notice how my name is x1, so make sure that whatever name this is, you type in that name. I'm going to type in box plot, and then I'm going to type in x1. And it gives me a box plot right here. Notice how in this box plot, it gives us my minimum, which is at 5, my maximum, which is at 19, my median at 10, my Q1, which is your first quartile, at 8, and then my third quartile at 18. And then looking at this, I can see that more data values are at the right. And since more data values are at the right, I could say that this box plot or these data values are skewed to the left, since more data values are on the right side. Another good thing about this is that I can actually find the mean of my box plot because I actually have data values now. So I could say mean x1 to give me the mean of 11.93. And you could also type in median for practice. Type in median, and that's going to give you 10, which we could see on the box plot. And since mean is greater than the median, I definitely know that it is skewed to the right, based off of my notes from the very, very, very beginning. If I could find it. right here. Since mean is greater than the median, it's skewed to the right. Now, that's not my question. My question is create the box plot. Well, remember that looking at my box plot right here, my minimum is 5, my maximum is 19, and my median is 10. So let's find a minimum 5, max 19, and then median 10. The only median I could see where it's 10 is actually C. It also gives us a minimum of 5 and a maximum of 19. So I also know that that works. Q1 of 8 and Q3 is 17, which we could also verify here, where this is 8 and this is 18. Now, let's say you wanted to find Q1, but you weren't given the box plot. You could also type in quartile, and then you want to name it, so X1, and then whatever quartile it is. 1 representing the first quartile. So your first quartile is 8. Your third quartile is 17. Now, if you click on or type in 2, that's the same thing as median. So the second quartile is the same thing as your median if you wanted to find your quartile. So 1, 2, and 3. 1 representing your first quartile, 2 is your median, and 3 is your third quartile. Number 16 is another table problem, so go ahead and pause this video, create your table, and make a linear regression. Once you make your linear regression, figure out which data point we need to exclude so that the result of the new linear model closely fits more. Remember, click on the magnifying glass right here, just so that you can see the data values. And you can see that there is some sort of outlier right here, because almost all of your data values fit that line. If I removed 8.2 and 24.3, notice how all my data values now actually fit perfectly on that line. So what point did we removed? Well, we removed 8.2, 24.3. That is essentially our outlier. Okay, number 17. A set of 9 data points is shown below, and we want to see what is true if 45 is added to the data set. Well, these data values right here are kind of close to each other. They're clustered. And if I'm adding 45, which is a big number, of course your mean is going to increase no matter what, because 45, well, it's a pretty large number. So thinking about that, I know that it can't be D. Now, like I said, you can think logically about this, or you can put this in onto the Dunswos calculator, find the mean, find the median, and see how 45 affects the mean and the median. But like I said, if I were to organize this, $45 is going to hit first, along with 3. So I know that my median might increase or decrease. Now the thing is, I'm not technically sure if it's going to increase or decrease or remain the same. So this question actually might be a good idea for you guys to actually put this into the calculator and see how my median gets affected. So you could type in median, x1, and right now my median is 9. The good thing about this is that if I add 45, my median is automatically going to change if, for example, if I say 1, my median changes to 8.5. So if I add 45, my new median is still 9. So my median actually stays the same. My mean increases because 45 is the big number, and my median stays the same based off of my table. Number 31, I have a table again. What's the meaning of the slope of the linear best fit equation of the data? Well, remember slope, y equals mx plus b, it's m. And if I think about m, this means that for every year, something happens to your slope. So it can't be A, and it can't be B. Because A and B actually deals with y-intercepts and not slopes. Well, it's either 6.7 or 0.2. I don't really know if it's 6.7 or 0.2. So your best bet is to plug this into the calculator and see if it's 6.7 or 0.2. So create your table, see what happens. y1, mx1 plus b, and this gives you your m and your b value. So m, which is your slope, is 0.20, and your b value is 62.69. So your equation is the same thing as saying 0.2 x plus y is equal to 0.20 x plus 62.69. So that means my slope increases by 0.2 each year. Number 32, the choices below are data sets, and the choices W is a constant. Each choice has the same mean. Which choice has the greatest standard deviation? So, if I wanted to find the greatest standard deviation, I should probably plug in a number for W. Don't really care what number it is, because either way, you're going to get the same mean. So let's just say that W is 7. So if W is 7, I know that this is going to be 5, 6, 7, 8, 9. B is going to be 5, 5, 7, 9, 9. C is going to be 4, 6, 7, 8, 10. And then a D is going to be 4, 7, 7, 7, 10. Now, looking at these data values right here, I don't really know which one is more spread out. So, I'm going to have to input these numbers onto Desmos to see if they have the highest standard deviation or not. And what I'm going to do is make a table with all the data values in it. So if I set that W was 7, this was 5, 6, 7, 8, 9. B was 5, 5, 7, 9, 9. And I'm going to say X2 for that one. X3 for this one is C, so that's going to be 4, 6, 7, 8, 10. And then X4 is going to be 4, 7, 7, 7, 10. You could ignore these by this. And then in order to find the standard deviation, what you're going to have to type in is STDEV. ST standing for standard, and then DEV for deviation. STDEV X1 gives us 1.5. STDEV X2 gives us 2. STDEV X3 gives us 2.2, and then STDEV X4 gives us 2.1. So your largest standard deviation is going to be C, which was X3 right here. So 4, 6, 7, 8, and 10. That's going to be more spread out than the rest. Number 33, we have Abby, and she scored 87, 80, 87, 93, 96, 89 on her first 4 history quizzes. What score does Abby need to get on her 5th quiz so that we have an average of 91 on her history quizzes? So I'm going to put this onto Desmos. Make a table for 87, 93, 96, and 89. Right now, her average, which is her mean, is 91.25. If we want a mean of 91, well, let's add in 90 and see what happens. If I were to add in 90, it actually gives us 91. So 90 is our correct answer. But if I were to look at 94, that's 91.8. If I look at 98, that's 92.6. And if I looked at 100, that's a 93. So I know if I were to play around, my mean is going to be a 91 if she gets a 90 on her next quiz. So it's a 90. "37. The table below shows the number of hours 7 students study for a math test and the grade each student earned on the test. How does Amanda's test score compare to the score predicted using the linear best fit model of data for a student who studied 3.5 hours? So, pause the video, make a table, make a linear best fit by using y1 squiggly mx1 plus b, and we're going to look what happens with our residual. Hit the magnifying glass, y1, mx1 plus b. Forgot the 1. And that's my regression line. Amanda's, if I were to look back again, is a 93. So Amanda's was 3.593. Okay, so Amanda's is right here, 3.593. Remember, by definition, the residual is the difference between my predicted value and my observed value. So if I were to look at Amanda's score, that's a 93. And if I were to look at the predicted value, that's going to be my intersection from my purple line and my green line, which is 94.674. So the difference from 94.674 and Amanda's 93 is about 1.674. And that's about 2 points. And looking at my residual, this means that Amanda scored 2 points lower than the expected score of the the regression line. Since Amanda's point is right here, and my line is above her point. So about 2 points lower than the predicted value. Now, I do want to comment about Patrick's because Patrick also studied 3.5 hours. Patrick's score is right here, which is a 95. And my predicted value is 94.674. So Patrick's expected score was about half a point higher than the predicted score. Number 40, we have Marcus, and we have the height and y of plants over the course of 3 weeks, x is days, and we know that the correlation coefficient is 0.85. What can be concluded about the correlation coefficient of the data? Well, I know that 0.85 is positive, and it's strong because it's greater than 0.5. So it can't be C and it can't be D because it's a weak relationship. We don't want that. So now we need to see if it is a height of the plant increases or the height of the plant decreases. Well, if my R value right now is positive, then I know that my graph should look something like this, which means that as we have the number of days increasing, I know that my height of the plant also increases, so it has to be A. B would happen if my value was negative, like that. So this would be B. But our answer for number 40 is A. Okay, number 46. The table below displays the walking heart rate and running heart rate of 8 girls and in beats per minute. And we want to find the predicted heart rate if we have a walking heart rate of 100 BPM. So we have a walking heart rate of 100 BPM. And we want to find out what the running heart rate is. Well, just plug this in and see what happens. So create your table. It tells you that it's a linear model. And since it's a linear model, you could just say y1 squiggly mx1 plus b to figure out what's up. And it's asking us what's the running heart rate if I have a walking heart rate of 100. So if I look at 100, this means that my running heart rate is going to be the intersection between my red and black line, which gives me a running heart rate of about 162.86, which if you round up, that's going to give you 163. So my running heart rate is 163. (47) We want to see what's skewed to the left, what's skewed to the right, and what's symmetric about the mean. There's two ways that you could look at this. The first way is go on Desmos, create a box plot, and see where your data values lie. Or if you were to look at your data values, look at what's happening. So notice how here I have 15, 25, 35, 45, 55, and then a big jump at 115. I have more smaller values on the left, and since I have more smaller values on the left, I know that this is skewed to the right. And then here, I have more data values on the right. Since I have more data values on the right, I have skewed to the left. And then here, 15, 25, 35, 45, 55, and 65, they're pretty even. And since they're pretty even, it's symmetric about the mean. And of course, you could verify that this is symmetric to the, not symmetric, this is skewed to the left, and this is skewed to the right by looking at the mean and median. So if I were to look at the mean of x1 and the median of x1, notice how my mean is greater than the median. And if I were to look back at my notes at the very beginning, mean greater than the median is skewed to the right. Oops. So that's why. The 15, 25, 35, 45, 55, and 115 is skewed to the right. So more data values on the left side gives us skew to the right. More data values on the right side gives us skew to the left. So it's just flip-flopped. And then if it looks symmetric, then it's symmetric around the mean. Number 15, we have a table and we want to find the slope of the line that best fits the data. If I want to find the slope of the line that best fits the data, I can plug it in and find my regression line. Do y1 mx1 plus b. Notice how your data values fit perfectly. So you could actually find the slope using algebra if you didn't want to use a calculator. The slope of my line is 0.03, and 0.03 as a fraction is 3 over 100. So it's B. '25, we have the table below that shows the area of several states. Right here, Delaware has an area of 2,000 square miles. What history of Delaware is included in the data set? Well, if this is thousands of square miles, I have to divide this by 1,000. So 2,000 square miles divided by 1,000 gives us 2. Don't know what's really going to happen. So we are going to create a table. Let's see what's going to happen. So right now I have a mean of 31.375. If I add in 2, that leaves me at 28.11, which means my mean actually decreases. So it can't really be A. My range, remember, is the lowest, the difference between your lowest and highest. So looking at this, my highest was 59, my lowest is 6, so 59 minus 6 is 53. But then if I have a Delaware being added in, which is 2, 59 minus 2 gives us 57. So your range actually increases, not decrease. So I also know that B is incorrect. Looking at C, I have my interquartile range decreases. Well, that's my IQR. In order to find my IQR, we're going to have to find out what Q1 is. And we're going to have to find out what Q3 is. And subtract that. 54 minus 10 is 44. But that's without Delaware. If we add in 2, notice how everything's going to change now. If I add in 2, I'm still at 44. So actually don't increase or decrease. Oh, wait, no. Let me do this. Let's set this as A. And let's set this as B. So that I can do B minus A. That's 44, okay. Now if I add in 2, notice how 44 now changes to 46.5. So my IQR actually increases because my IQR, my quartile 1, decreased. So it can't be C. The only one that's solved, standard deviation increases. To figure that out, I'm going to look at the standard deviation. It's at 23.71, and then if I include 2, it's at 24.24. It kind of makes sense because 2 is basically an outlier, which means that it's not going to be within this cluster right here, which means that your data values are going to be more spread out because you included a 2 in your data set. So 25 is D. '26, we have a table And we want to find the meaning of the slope of the linear model for the data. Well, we remember that slope, anytime you see slope, you have to think per or every. So we have the car travels every 5 minutes, travels 5 miles every minute. The car travels 4 miles every minute. The car travels 4 miles every 5 minutes. And then the car travels 5 miles every 4 minutes. Well, I don't know what's happening. Meaning I have to find my slope using my regression line. Oop, forgot the 1 again. Y equals y1, mx1 plus b. Your slope is 0.8. So this means that it can't be A or B because the car travels 1 mile for every 0.8 of a minute. And if I think about that, 0.8 is the same thing as 4/5. So that means that the car travels 0.8 minutes every minute, or you could say that it travels 4 miles every 5 minutes, because if I multiply that 0.8 by 5, I'm going to get 4. So car travels 4 miles every 5 minutes. Okay, 36. We have the number of points scored by a basketball player in the first 8 games. And what happens if we add 24, 22, 27, and 28 with the data? So I'm going to add 15, 35, 18, all of those onto the table. And then I want to see what is happening with my standard deviation. So my standard deviation is now 7.67 for my original. What I'm going to do for x2 is actually do the same thing, but now I'm going to add my 4 data points that were listed. 24, 22, 27, 28. And my data value, once I do that, my standard deviation is 6.3, which means that it becomes less widely spread out. So which means my data points are less spread, which means it's closer to my mean. So it can't be A and it can't be D. Now we need to see if it's less peaked or more peaked. In order to figure that out, I actually need to make a histogram based off of my first data set, which is x1, and my second data set, x2. In order to make a histogram, well, you could just type in histogram, and it's going to make a histogram for you. Now, whenever you are making a histogram, though, you want to make sure that your bin width isn't 1. Make sure that it's 5, so that it looks something like this. 5 basically represents your bin width, which is your interval. I want to do the same thing for x2. Now notice how I have the same histogram with x1 and x2, but with x2, notice how it's more peaked right here in the middle. So here is x1, and then if I were to look at x2, it's more peaked, it's higher. So that's why for this one here, my distribution would be more peaked because it's more higher and less spread. (37) we have a table with shoe size and ages. Approximate what percent of the boys' ages is more than 1 year different from the age predicted by the line of best fit. I'm gonna make a line of best fit again. Create your table. Create your line of best fit. Have your age. And then create y1 mx1 plus b. And now it says, the question asks, what percent of boys' ages is more than 1 year different from the age predicted by the line of best fit for the data? This essentially means that where is my residual greater than 1? And remember, my residual basically means how far it is from my regression line and my data points. So you're basically trying to find the difference from here to here, here to here, here to here. And if I were to look at my data points more closely, I could only see 1, 2, 3, 4, where they are definitely going to be more than 1 compared to my prediction. Because from here, 6, 11, well, if I were to predict 6 on my regression line, it's about 10.8. Here at 9, I could predict 9 at 14.2, which is about a 0.7 difference. Here at 10, 16, at 10 is 15.3, so that's also a 0.7 difference. From 12, 17, 12 is about 17.6, 17, so that's about a 0.6 difference. So I don't want that. I do want this, and this, and this. So that's about 3. There are 7 data points, so I want to say 3 divided by 7 because those 3 has a residual greater than 1, which means about 42% of the boys' ages gives you a prediction of more than a 1 year difference. (38) What describes the relationship between the numbers of arithmetic errors on the students made and the amount of time the students took to complete the quiz? Notice how here, if I were to create a line of best fit, it's going to go down. Now notice how my line right here actually follows through and maps on these points right here. This is a really good indicator telling me that it is going to be a strong relationship. So it can't be C and it can't be D. Well, since my slope is going down, I know it has to be a negative relationship, so it's B. It's strong because my indicator says that all of my points are basically near my line. Besides this one here is a little outlier. But it's a strong negative relationship. 50, we have an elevator that can hold a maximum of 1,500 pounds. 8 people need to use the elevator. Bill had some measures from the data set of how much each person weighed. Which measure would be most useful to determine if the people can safely use the elevator? Well, thinking about this, the only one that really makes sense is the mean. Because if I have 8 people, I have to do 1,500 divided by 8. And that's going to give you about 187.5 pounds. This tells me that a person needs to weigh, on average 187.5 pounds if there are 8 people on the elevator. The median really doesn't make sense. The mode also doesn't really make sense because, mode's most. And then the IQR, that's your middle 50%, really also doesn't make sense. (18) We have a scatter plot, and we want to see the difference between the observed value and the predicted value at 88. Well, the observed value right now is 1497, and my predicted value at 88 is whatever 88 is whenever we plugged in it in there. So this is a question about residual, aka what's your difference between your predicted and your observed value. What I'm going to do is type in 518x minus 43886. I'm going to plug in x as 88. Or I could plug in 88 in here. And that gives me 1698. Now, 1698 is my predicted value. 1497 is my real value, so I want to find the difference between 1497 and 1698. Which gives us 201. So my difference between 1698 and 1497 is 201, which is the definition of a residual. We have a monthly average of electric bills between 98 and 2005. According to the line of best fit, approximately how much per month would the Smiths pay in 2007? What we're going to do is plug this into the table. And then the good thing about the Desmos is that it automatically fills in the table for you, which is pretty nice. Magnifying glass, 1, mx1 plus b. And it says 2007. So I'm going to look at 2007 and find my intersection between my green and blue line. Gives me about $133.72, which is about 134. So 17 is A. We have 5 students in Ms. Brown's algebra class. According to the line of best fit, what is the predicted test score of a student who studied 1 hour for the test? So I want to see what is the test score for 1 hour. Well, like I said, when in doubt, if you have a table, put it in the calculator and make your regression line. squiggly mx1 plus b. We want 1 hour, so x is equal to 1. Find my intersection. And a person who studied for only 1 hour is going to get a test score of about a 78. So 16 is B. We have another table, and we want to see how many fat grams would be expected if we have a 275 calorie order of fried chicken. Well, once again, make a table. Like I said, at the end of this video, whenever it is, you're going to be experts at stats now, especially on making a table and using y1 squiggly mx1 plus b. That's for sure. We want 275, so x is 275. This means that there are about 25.31 fat grams. So 25.31 is C. Now, sometimes on the EOC, they are going to give you 3 box plots like you saw on the miles per gallon question with the family, sport, and small cars. This is another question. We have fertilizer, and Delea is growing tomato plants. And we want to see which fertilizer is the best that she could use. Well, looking at this, I wouldn't pick fertilizer A because the plant height is from 1 to 8. Not that great. Fertilizer B has a very big standard deviation or a very big spread, a very big IQR. So your tomato plants are going to range from 6 to 17, which isn't really consistent. I would prefer C because your plant height is going to be from, let's say, 10 to 16. They're pretty close to each other. They're consistent. So you know that all for tomato plants are going to be within that range of 10 to 15. Now, since they actually give you data values right here, you could actually find the average of the data values. But notice how on B, your box plot kind of looks symmetric, which means that your mean is going to be equal to your median. Now, fertilizer C here, notice how most of my data values are on the right. And if it's on the right, this means that I'm skewed to the left. And then I think A, if you were to look closely enough, you have more on the left, so it's going to be skewed to the right. Okay, this is just another example. I'm not going to go over it. It's another plug and chug on the table. You should know how to do it by now. But I do want to go over these two problems. Sometimes on the EOC, they are going to ask you what's best. So is a linear function the best, a quadratic function the best, or an exponential function the best? And at the very beginning, I told you how to create a regression line using a linear function and an exponential function and a quadratic function right here. Now, over the past hour, we've been focusing on linear functions, but for the next 5 minutes or so, we're going to look at exponential functions and how to write them. We know with an exponential function, it looks like the form y is equal to ab to the x power. So looking at this one right here, if I look at the exponential function and I want to see how many hours will it take for 200 nats to gather, I have to create a table. And after creating the table, instead of y1 squiggly mx plus b, I'm going to use a different formula because I have to use an exponential function now instead of a linear function. Notice out here, it kind of looks like it's going to curve up. So you know you're going to have to use an exponential function. So this is what my exponential function looks like. y1 squiggly ab x to the first. And I want to figure out how many hours will it take for 200 nats to gather. Well, nats are my y values. So instead of x, I'm going to say y is equal to 200. And figure out that it's going to be about 6 hours for the nats to gather to create 200 nats. So that's what you would do for an exponential regression. Very similar to linear, except you have to remember that it's y1 squiggly ab to the x1. This one right here, we have an experiment, 300 pennies were shaken, and write a function readjusted by the context. Use the context to explain all values of the function. How are those values reflected in the table? So put this on the calculator. And let's say that we didn't know that it was an exponential function. Once you create your table and look at the table and the dots, it's actually going to show you that it kind of looks like a exponential function since it's curving down. A linear function would not be the best for this one. So you do y1 squiggly ab to the x1. And you could see that my regression line is 301.919 times 0.54 to the x. 546 to the x. 301.19 represents your starting value, so the number of row would be 0, and then after each row, about 54% of them is lost. So that's your common ratio, 0.54. Same thing with this one. The answer is 116. You're going to do an exponential function. So y1 squiggly ab to the x1. Do that to get 116 for 15 minutes. 15 minutes is x, so make sure that you do x is equal to 15, and then find your intersection. I'm not going to do that one, but you can on your own. Point 32, I know that since 0.32 is positive, it can't be B or D. And since 0.32 is less than 0.5, I know that it's a weak positive relationship. Okay. That was definitely more than an hour. So hopefully by this hour, you are experts at stats. Basically, as long as you know how to put everything in a table and just analyze it, you'll be good. Okay, good luck on your final. You guys will do great. Remember, science is about 18 to 20% of your final exam, so it's a lot.